Welcome to the presentation of database transaction management. In the world of databases, managing transactions is crucial to ensuring that data remains accurate, consistent, and secure. This presentation will walk you through what a transaction is, the principles that govern reliable transaction, and the asset properties that help maintain data integrity even in the complex or concurrent environments. So, a transaction in a database management system is a sequence of one or more operations that are treated as a single logical unit of work. The operation could be involve reading, writing, or modifying data. The idea is that a transaction should be completed in a full. If any of the process fails, the entire transaction should be rolled back. This ensures the database remains consistent and prevents partial update or any errors. So the transaction is ruled from the ACID properties. So ACID stands for atomicity, consistency, isolation, and durability. So in short, atomicity is about all or nothing. Will uh, deep dive this concept in the next slide one by one. But in short, atomicity is all or nothing, and consistency is all about the data correctness, meaning that the data has to stay correct before and after the operation. And for the isolation, transactions don't mess each other up. So every operations should be isolated from each other. And for the durability, it is about the durability of data, meaning once the data is saved, it stays saved even in the hardware or the network failure case. These all rules help databases stay reliable. So let's have a look for all of this principle one by one. So for the atomicity, this means that a transaction is like a single action, even if it has many steps. If one part of it doesn't work, the whole thing gets undone. For example, if you try to send money on your phone dies halfway, the transaction won't go through at all. It roll back so your money doesn't just disappear. So for if a person A transfers money to transfers B, if it is there's a error like hardware or network error. So if the money is withdrawn from the person A but it is not deposited to the person B, that won't be a accurate transaction. So what atomicity ensures us is that the operation should be done at all. If it is done like half, it should be rolled back, and all the transaction should be rolled back, and it should be from the step first. So no partial change are on the database. So for the consistency, it makes sure the database follows all the rules all the time. If the transaction tries to do something that breaks a rule, like putting a letter in a number field, it won't be allowed. The database always has to be in a correct state before and after transaction. The data must follow all integrity rules before and after a transaction. So for the isolation is all about keeping transactions from interfering with each other. If you and someone else are doing something at the same time, your transaction won't see each other half done work. It's like taking turns even if things are happening at the same time behind the scene. So for example, if there is a single product in e-commerce side, and if two users concurrently tries to save the product in the cart, then two users will have the same product in the cart. But that's not true because there will be a single product. So isolation ensures that the transactions are executed independently, right? So without interfering from each other's transaction. So by following the isolation logic, each of the user transactions or the operation will be isolated. So that makes the data accurate and the operations also accurate. So for the durability means that once the database says the transaction is complete, the change is permanent even if there are software or hardware failure like system crashes right after the operations. It's saved in a way that won't be lost. It's like kind of pressing save on a document after writing it, right? So if once the data is saved, then the data should be durable for like in a persistent way. By that way the customer data won't be lost at all. Till now we have understand the transaction concept in database system. We should follow the ACID properties to properly implement the transaction in database system. But with the rise of the distributed system architecture like the microservices, there can be different databases for different service or nodes. So as you can see in this picture, there's three different databases and three different services for a single application, where order service have its own database, inventory have own database, and authentication have own database. Being different database, but these two database needs to perfectly coordinate with each other, meaning that when order is created, inventory should be deducted or should be updated after the order. If it fails to do so, that will not be a proper transaction, meaning that will have some inconsistency in the database. So now we have a situation where we don't have a single database, we have a different database. Now it will be hard to achieve the transaction, in contrast to the traditional monolithic database where we have single database and we can implement the transaction with the code given by the ORM or the query given by the SQL. Now let's see what problem is there in the distributed management system for the transaction or the communication. So we'll look into this problem, widely known as two generals problem, where two generals sit far from each other in a separate valley, but they have to attack a city which is in between them. Now they need to attack at the same time, because if they attack separately they will lose the war, and they have to attack at the same time. But there can be a there is not the proper communication method with them, so they have to send the messenger to communicate with them. But the problem is that the messenger needs to go through the enemy base, so the messenger can get caught, and the uh, message might not get to the general from one general to another. So let first look at this scenario. The general one sends a message to the general 2 saying that let's attack on Monday. Now the general one is in confusion if the general 2 get my message or not. Now if the general 2 gets the message from the general 1 and he acknowledges it and he sends OK to general 1. Now general 1 receives the message, but general 2 is in the same situation. Now general 2 is in confusion that if general 1 receives my acknowledgement or not. Now again general 1 sends the message, yeah, I have received your acknowledgement, and again the general 1 is in the same place or the same confusion with that was with the general 2 before. So this goes on with the continuation. It shows that there might not be a proper coordination if the message sent between the two nodes or the two parties have the unreliable communication. So the same applies with the distributed system, because distributed system are separate from each other and they have to rely on the communication, they have to coordinate with the communication over a network. So network calls are dependent on the hardware. There can be hardware failure, and there can be many cases with the network or the software itself. So this shows how the problem with the distributed system is. So to mitigate the issue, there are different patterns in the distributed system to reduce the problem faced by the two generals. So after seeing the unsolvable nature of the two general problem, so now let's discuss a practical protocol that works under assumption uh, two-phase commit. The protocol in the distributed system, it ensures atomicity in distributed transaction, meaning that all the nodes commit or abort. So this is the diagram for the two-phase commit. So the two-phase commit is mainly within the two phase. First one is prepare phase, where all the coordinator sends prepare message to get prepared for all the participants, all the node, uh, where each participant log resources, perform checks, and replies okay uh, if the system is ready to commit, or about if the failure occurs. This is same like the generals agreeing on attack, but with acknowledgement, obviously. And for the phase 2 commit or abort phase, if all participants says okay, the coordinator sends commit, otherwise it sends abort. Unlike the two generals problem, two-phase commits block if all coordinator fails. Uh, After prepare a trade-off for consistency. So two-phase commit assumes reliable channel using the retries and timeout, while the two generals problem assumes arbitrary message loss. So let's look into the another approach to mitigate the issue in the distributed system. To mitigate the issue faced by the two-phase commit and the problem of the generals, there is another protocol called saga pattern for the distributed system. The saga pattern provides an elegant solution to the distributed transaction by decomposing them into a sequence of logical transaction. Uh, as we can see in this picture is from the Chris Richardson blog from microservice.io. So in saga pattern, each nodes is paired with the compensating actions. Unlike two-phase blocking all or nothing approach, Saga executes steps sequentially. If any steps fail, predefined compensating transaction or the undo prior operation. This asynchronous non-blocking design is ideal for long-running processes like the e-commerce orders, where service may be temporarily unavailable. So in Saga pattern, there is a critical role played by the message broker. As you can see in the middle of these pictures. So the message broker like Kafka or RabbitMQ is the backbone of Saga orchestration, where it decouples the services by enforcing async communication between order service and customer service, which provides the delivery guarantee with the retries failed messages, like the reserve credit command, um, which compensate coordinates with the route failures, event to triggers, rollback workflows. Uh, so as we can see in the picture, order service creates an order, emits event to the broker, while the broker routes reserve credit command to the customer service. If reservation fails, broker propagates a failure event, trigger compensating cancel order transaction. So the advantages of the saga pattern over the two-phase commit is that there is no single point of failure. We have seen the coordinator, there was a coordinator in the two-phase commit, uh, which is replaced by the broker as a centralized coordinator, and the two-phase commit using the message broker. This is a non-blocking via async messages, which is scalable and which can be recovered easily with the broker persist message for the crash recovery. So this is all about the saga pattern for the distributed system. It obviously does have the trade-off, which is there is eventual consistency. Transaction complete asynchronously in the saga pattern, but this is acceptable for most of the businesses. So yeah, as we have seen, there will be an unsolvable problem with the distributed system like the two generals problem, but there are ways to mitigate the issue with the protocols. So it's all about the trade-offs when we need to use one service, one protocol in contrast to other. So this is how the transaction is done in the distributed system, like two-phase commit and the saga pattern. So this was about the transaction management in database system. Transaction management is easy while we work on single database like in monolithic architecture, but it becomes harder and harder when we have the uh, vast requirement, we need to decouple every services, so it becomes relatively harder than the monolithic database. But there are several approaches to mitigate the issue in the distributed system to make the transaction apply all the ACID properties. So this is about handling database transaction uh, in the both distributed and the monolithic architecture. So this is all about it. Thank you.